Section 5.3 is about proving a quadrilateral is a parallelogram. So we're going to bring proofs back into this section. Okay, they're going to kind of come up every other section now, but pretty much we're just kind of building on what we learned in chapter 3 about proofs. So to prove a quadrilateral is a parallelogram, you have to prove one of the following. You either have to prove that both pairs of opposite sides are parallel, or you could prove that both pairs of opposite sides are congruent, or you can prove that one pair of opposite sides are both congruent and parallel, or you can show that both pairs of opposite angles are congruent, or that the diagonals bisect each other. Okay, so what does all that mean? Hopefully some of that information that I just said will become clearer with this picture right here. So which information is not enough to prove ABCD is a parallelogram? So for choice A, they have AB is congruent to CD and AB is parallel to CD. That's one pair of opposite sides that is both congruent and parallel. And again, if you were to scroll back up, that was one of your choices. So that is enough information. Again, we're looking for the one that's not. So let's move on to choice B. Choice B is that AB is congruent to CD and BC is congruent to DA. That's both pairs of opposite sides are congruent. Again, if you scroll back up, that is one of your choices to prove that something is a parallelogram by showing both pairs of opposite sides are congruent. So that is a way to prove that they're congruent. Again, we're looking for the way not to show they're congruent. So for choice C, we have AB is congruent to CD, and we have that BC is parallel to AD. That's your one that's not enough. Again, if you scroll back up to the 5 ways to show that it is a parallelogram, you would need one pair that is both parallel and congruent. Here you have two different pairs. One pair is congruent, one pair is parallel. That is not a way. Okay, and just to show you the last one here, hey, AB is parallel to CD and BC is parallel to AD. That one's both pairs of opposite sides are parallel. And again, that is enough information to show that they are parallel. Okay, so here we go with doing a proof involving a parallelogram. Okay, so pretty much the same rules for proof are going to hold true. Givens are always going to go into first statement number 1, and your proof is always going to be your last statement. So again, if I want to prove that ABCD is a parallelogram, I have to show one of those 5 things that we just talked about on that first slide. So either both pairs of opposite sides are parallel, both pairs of opposite sides are congruent, one pair of opposite sides are both congruent and parallel, both pairs of opposite angles are congruent, or the diagonals bisect each other. Okay, so again, just like in the previous chapters, we need our statements and our reasons. And again, going in for number 1, I have AB is congruent to CD. And angle 1 is congruent to angle 2. And the reason I know they're true is because it was given. So again, I'm going to mark that off in my picture. AB is congruent to CD, and angle 1 is going to be congruent to angle 2. There are a ton of different ways to prove this. I'm going to do it what is the easiest way. It might not be the most obvious, but it's the easiest. Okay, if angle 1 is congruent to angle 2, again, these would be parallel lines cut by a transversal, and those are alternate interior angles. So if the alternate interior angles are congruent, that's going to mean that DC is parallel to AB. So in one step, I can show you that I have that parallelogram. So we're going to say that they're parallel, and then it's going to be a parallelogram because I have one pair of opposite sides that is both congruent and parallel. So again, I'm going to say DC is parallel to AB, and that is because alternate interior angles are congruent. And again, now I can say that ABCD is a parallelogram. And again, the reason it's a parallelogram is because you have one pair of opposite sides that's both congruent and parallel. Okay, other ways that you could have done it, hey, if you wanted to, again, this might have been more obvious, but it just would have taken more steps. You could have ended up proving the two triangles are congruent, the triangle on the top and the bottom there, and then you could have used CPCTC to say that the two sides were equal, and you could have done it by both pairs of opposite sides are congruent there. Okay, if you also use that, the two triangles, you can end up saying that the this angle would be congruent to this angle, and then you'd have, again, a pair of parallel sides. So again, you could have done another pair of parallel sides if you wanted to. You could have said both pairs of opposite sides are parallel, or both pairs of opposite sides are congruent. So there's more than one way to do it. Okay. For 3, now this time around, we're given the parallelogram. So if we're given a parallelogram, we can use the properties of a parallelogram inside of a proof. Kind of like if they give you perpendicular lines, we can use that inside of a proof and say that perpendicular lines form right angles. We can do the same thing with the parallelogram. We can use those properties as reasons. So let's see what we have given and what we want to prove. So I have parallelogram ABCD. So I'll highlight the entire parallelogram in red. All right, so that is your parallelogram, and I'm told that AE is congruent to FC. Okay, now notice AE and FC are not the entire sides of the parallelogram, just to be clear. And eventually I want to prove that AF, this piece here, is congruent to EC, which is going to be that piece there. Okay, I'm going to erase the ones that we weren't. That's what I want to prove, just so we don't think that that's part of the proof. Okay, so now we have our statements and we have our reasons. Okay, so I think what I'm going to do is if I can somehow show that this triangle and this triangle are congruent, then I'll be able to say that AF is congruent to EC because of CPCTC. Okay, so let's try to do that. First thing, again, that I know is that I have parallelogram ABCD, and AE is congruent to, oops, on the wrong side, is congruent to FC, and the reason I know that that's true is because it was given. Okay, the next thing that I'm going to say, I can say that AD is congruent to BC. Why? Because again, that whole red figure is a parallelogram, and opposite sides of a parallelogram are congruent. So I'm going to say that AD is congruent to BC, and that is because opposite sides of a parallelogram are congruent. Okay, so you can draw your little picture for a parallelogram. So opposite sides of a parallelogram are congruent. Okay, other things I know about a parallelogram, opposite angles are congruent. So that means if I start with angle D, directly opposite that is going to be angle B. So now I can say that angle D is congruent to angle B. And again, that is because opposite angles of a parallelogram are congruent. Okay, now, got to be careful also. Hey, that red hash mark again represents AE. It does not represent the purple side of the triangle or the whole side of the parallelogram. So the next thing that I'm going to do is I'm going to first say that the entire sides of those two parallelograms are going to be congruent, that pair of opposite sides, because again, opposite sides of a parallelogram are congruent. And now we're going to see the subtraction postulate come into play. I don't need the entire side. I need this part right here, the EB. So if I have the whole side and I get rid of that part, then I can use subtraction and I'll be left with EB. So that's what I'm going to say. I'm going to say first that the entire side AB is congruent to DC. And again, that's because of opposite sides of a parallelogram are congruent. Hey, just so you know, I could have added that into step 2 if I wanted to, but I wasn't seeing that right when I was thinking about how I was going to do this proof. So if you do it in 2 different steps, that's completely fine. Okay, and now we're going to use that subtraction postulate. So I am literally taking step 4 and I'm subtracting out the givens from here. So I'm taking AB and I am subtracting out AE. When you do that, you're going to be left with that piece right there, the EB. 3 hash marks through it. Okay, and on the other side, we're going to do DC minus FC. And when I do that, I'm going to be left with DF. That's that piece over there. And the reason that that's true is subtraction. Okay, I'm not sure that subtraction has ever come up inside of a proof before, but now it has. And when it does, it's the key. Again, when I actually subtract, that's EB that you're left with and DF. Okay, and the reason, again, I substituted. Okay, all I did was take out that and said what its equivalent was. Take out that, say what its equivalent is. So that's substitution. Okay, now I believe I have enough information to prove the 2 triangles congruent. I have a side, I have an angle, and I have a side. So triangle AFD is congruent to triangle EBC, and that is because of side, angle, side. And now finally I have enough information to say that those 2 pieces right there with the 4 hash marks through are congruent. So AF is congruent to EC, and that is because of CPCTC. And our last one for today. So we have parallelogram ABCD with diagonals AC and BD that intersect at E. So basically all they've told me is that I have a parallelogram. Okay, and I want to prove that ACD, this angle here, is congruent to CAB, which is going to be that angle there. Okay, so statements. And my reasons. Okay. And again, the only thing again that I was given was parallelogram A, B, C, D. Okay. So the easiest thing to do here, which would be very boring, I'm going to end up doing it a longer way, but just real quick. Hey, you know if ABCD is a parallelogram, that this side is parallel to that side, and the 2 angles in question are alternate interior angles, and alternate interior angles are congruent. So literally for step 2, you could say DC is parallel to AB, and then you can say your 2 angles are congruent because alternate interior angles are congruent. But that would be boring. Okay, so let's do it a little bit of a longer way. So again, I was given that parallelogram. The next thing that I'm going to say is that DC is congruent to AB. I feel like you see the congruent things a lot easier than you see the parallel things. So that's why I'm going to do it a little bit of a longer way. So DC is congruent to AB. And again, the reason that's true is because opposite sides of a parallelogram are congruent. Okay. The next thing that I'm going to say is I was given the diagonals, and we haven't really talked about the diagonals yet, so let's use the diagonals inside this proof. So what am I going to say here? The diagonals of a parallelogram bisect each other. So what does that mean? That means that DE is going to be congruent to EB, and that AE is going to be congruent to EC. Okay, and again, that's because the diagonals bisect each other. Hey, remember, I don't have those angles yet. Let me get rid of them. That's what I want to prove congruent. I don't have them yet. All right, so DE is congruent to EB, and AE is congruent to EC. And again, that's because diagonals of a parallelogram bisect each other. Okay, now I have enough information to say that this triangle is congruent to this triangle because of side, side, side. So triangle AEB is congruent to triangle DEC. And again, that's because of side, side, side. And now finally, I can say that those two angles are congruent, this angle and that angle. Why? Because of CPCT. So angle ACD is congruent to angle CAB because of CPCTC. Again, I could have done that in one step, but again, I feel like a lot of times the parallel information is a little bit harder for you guys to see. So even though this way was longer, I feel like it's easier for you to see the opposite sides are congruent, and we hadn't shown a problem with diagonals bisecting each other yet. So now you have that.